How can a $10 billion telescope orbit absolutely nothing? The mind-bending reality of the James Webb Space Telescope, humanity's most advanced eye in the sky, is positioned at what scientists call Lagrangian point 2. While planets orbit stars and moons orbit planets, Webb performs a cosmic ballet around an invisible point in space, a mathematical concept rather than a physical object. Picture this engineering marvel silently dancing around emptiness, defying our everyday understanding of gravity. This represents one of the most unusual orbits in our space exploration history. The cosmic ballet, understanding Lagrangian points. Imagine standing at a cosmic crossroads where the gravitational forces of giants create perfect harmony. In the intricate dance between the Sun and Earth, 5 unique locations emerge where physics creates something extraordinary: Lagrangian points. Named after the 18th century mathematician Joseph Louis Lagrange, these points represent something almost magical. Places where a small object can maintain a fixed position relative to 2 massive bodies. These Lagrangian points function like cosmic anchor points in the vast ocean of space. Picture the universe as an enormous dance floor where the Sun and Earth perform their celestial waltz. Their combined gravitational influence creates these 5 unique spots: L1, L2, and L3 along the Sun-Earth line, while L4 and L5 form equilateral triangles with them. Each point offers a unique gravitational signature, much like how a bead can rest perfectly on a curved string, neither sliding down nor floating away. The Webb telescope resides at L2, approximately 1.5 million kilometers from Earth, so distant that radio signals take 5 seconds to travel each way. This location serves as a perfect cosmic rest stop, allowing the telescope to orbit the Sun at exactly the same time as Earth. Webb travels in formation with our planet, maintaining the same yearly orbit while using Earth as a shield against the Sun's harsh glare. L2 isn't a physical entity you could visit and plant a flag on. Instead, it's a mathematical solution to a complex gravitational equation, an invisible node where forces balance precisely, allowing Webb to maintain its solar orbit with minimal fuel consumption. Physics creates a gravitational landscape resembling hills and valleys in space-time. L1, L2, and L3 are like mountain saddles, places of precarious balance where objects can temporarily rest, but drift away if disturbed. L4 and L5 form gravitational valleys where objects naturally collect over time, pulled toward rather than away from stability. Webb's position near L2 provides extraordinary advantages for astronomy. From this strategic vantage point, the telescope simultaneously keeps its back to the Sun, Earth, and Moon. This alignment allows its tennis court-sized sunshield to block heat and light, creating the frigid conditions its infrared instruments require to observe the universe's most distant reaches. The brilliance of this positioning becomes evident when considering alternatives. If Webb orbited Earth directly like Hubble, it would cycle between extreme temperatures, making consistent observations impossible. The thermal stability at L2 allows Webb to maintain the steady -233 degrees Celsius, -387 degrees Fahrenheit temperature. Its sensitive instruments need to detect the faintest infrared signals, transforming our understanding of the cosmos with uninterrupted clarity. Dancing around emptiness, Webb's counterintuitive halo orbit. While the thermal stability at L2 creates ideal conditions for Webb's mission, a fascinating truth challenges our fundamental understanding of the telescope's position. The James Webb Space Telescope isn't sitting at L2 at all. Instead, it performs an elaborate orbital dance around an empty point in space, following a path so vast it makes the Moon's orbit around Earth look modest by comparison. This counterintuitive reality surprises most people. Rather than residing directly at L2, Webb traces what engineers call a halo orbit, an elliptical path circling a mathematical abstraction, like a dancer perpetually circling an invisible partner. This orbit varies between 250,000 and 832,000 kilometers from the L2 point itself. At its furthest point, more than twice the distance of the Moon from Earth, the telescope essentially orbits nothingness, a point that exists purely in equations rather than physical reality. Why would NASA engineers deliberately position a $10 billion marvel in a bizarre orbit? The answer lies in the delicate balance of competing priorities. This carefully calculated trajectory allows Webb to remain perpetually in the shadow of its sunshield, while keeping the Sun, Earth, and Moon aligned on one side. If Webb orbited directly at L2, it would regularly pass through Earth's shadow, cutting off the sunlight needed to power its systems and the communication signals essential for transmitting its precious data back home. The halo orbit creates what physicists call a dynamic equilibrium, a perpetual state of controlled falling where Webb never truly settles. Like a cosmic tightrope walker circling an unseen central post, the telescope experiences a constant tug-of-war between the Sun's and Earth's gravitational pulls, along with centrifugal forces that combine to create this unique trajectory. Webb remains in continuous motion, never reaching a final destination. This elaborate orbital path centers not precisely on L2, but on a slightly offset point called L2' that shifts slightly toward Earth. Webb completes one entire circuit around this invisible focal point every 6 months, varying its speed throughout the journey as gravitational influences shift. This orbital strategy directly influences Webb's longevity. By placing the telescope in this expansive halo orbit, rather than trying to park it directly at L2, engineers have significantly extended its operational lifespan, as objects positioned farther from gravitational focal points require less energy to maneuver, a principle that later impacts Webb's station-keeping requirements. Throughout this journey, the telescope must constantly adjust its orientation, carefully managing the angles of its sensitive instruments to prevent stray light from Earth and the Moon from contaminating its observations. This requires precise communication scheduling and continuous adjustments, a testament to the extraordinary planning behind Webb's mission. The cosmic tightrope, Webb's battle against chaos. While those continuous adjustments appear graceful from afar, a hidden battle rages behind the scenes. Every 21 days, a team of NASA engineers performs a high-stakes maneuver to prevent humanity's most advanced telescope from drifting into oblivion, all while conserving precious fuel that determines Webb's ultimate fate. Imagine balancing a pencil perfectly on its tip, essentially what's happening with the James Webb Space Telescope at L2. The slightest nudge would send it tumbling. In Webb's case, those nudges come constantly from all directions. Solar radiation pressure, the physical force of sunlight, relentlessly pushes against the massive sunshield, creating torque that gradually destabilizes the telescope. The gravitational tugs from the Moon and planets combine with Webb's movements between observation targets to create orbital perturbations that compound over time. The Flight Dynamics team is Webb's vigilant cosmic custodians at NASA's Goddard Space Flight Center. Through the Deep Space Network, that global array of massive antennas in Australia, Spain, and California, they precisely track the telescope's movement. These ranging measurements reveal Webb's exact position and velocity, allowing the team to detect even microscopic deviations from its intended path. Each thruster burn is a delicate operation. During a typical correction, engineers fire thrusters for mere seconds, applying forces measured in micronewtons, equivalent to the weight of a small ant pressing down on your palm. Yet, these tiny pushes, almost imperceptible by everyday standards, mean the difference between scientific discovery and catastrophic drift. The telescope slowly responds, shifting its position by millimeters in the vast emptiness of space. What makes this orbital maintenance so challenging is the finite nature of Webb's fuel supply. Every gram of propellant used directly reduces the telescope's operational lifespan. This creates a perpetual tension, maintaining precise positioning while maximizing mission duration. Engineers must predict Webb's trajectory days in advance, calculating exactly how much thrust to apply and in which direction. A cosmic chess game where nature makes unpredictable moves. The paradox at the core of Webb's station keeping is that maintaining perfect stillness requires constant movement. Without these carefully calibrated interventions every 3 weeks, the telescope would drift away from L2 within months, rendering its revolutionary instruments useless. This relentless battle against cosmic forces exemplifies the hidden heroism behind Webb's headline-making discoveries. While the world marvels at unprecedented images of distant galaxies and alien worlds, few recognize the team of engineers performing this cosmic maintenance. These unsung guardians ensure that Webb appears effortlessly suspended at its gravitational sweet spot. Engineering for the void, surviving at the edge of nothing. Beyond the elegant orbital maneuvers lies an even more incredible engineering feat, creating a telescope that can survive in a cosmic environment so hostile it would destroy conventional technology in hours. At L2, Webb essentially exists in two worlds simultaneously. One side bathed in constant sunlight, hot enough to boil water. The other facing the infinite cold of the cosmos, at temperatures approaching absolute zero. This thermal battleground spans a staggering 200 degrees Celsius range, a testament to the extreme conditions Webb was built to endure. The heart of Webb's survival strategy is its remarkable sunshield, a technological marvel that deserves closer examination. These 5 gossamer-thin layers of capped-in film create a thermal gradient that would be impossible in Earth's atmosphere. Each layer progressively blocks and redirects heat, with microscopic gaps preventing heat transfer by conduction. The execution represents engineering precision at its finest. These nearly weightless sheets had to unfold flawlessly after being tightly packed for launch, with over 10,000 individual components working in perfect harmony. Like a master watchmaker assembling a grand complication, engineers created a system where a single torn layer or stuck deployment mechanism would have doomed the entire mission. Imagine trying to power a sophisticated scientific laboratory using the equivalent of a small household solar array, but with sunlight only 4% as intense as what we receive on Earth. Webb's innovative power system generates a modest 2 kilowatts that must be meticulously budgeted across all systems. This power limitation shapes every aspect of the telescope's operation, from the scheduling of observations to the precise management of instrument heating. Engineers have crafted systems that function reliably for decades despite these constraints, ensuring Webb can fulfill its cosmic quest. The communication system transmits extraordinary volumes of scientific data across the vast emptiness separating L2 from Earth. The high-gain antenna achieves transmission speeds of 28 megabits per second, despite the signals traveling 1.5 million kilometers through space. This data pipeline is the telescope's lifeline, connecting humanity to the universe's deepest secrets. What truly separates Webb from conventional spacecraft is its unforgiving operational environment. Unlike missions to the International Space Station or the Moon, Webb operates beyond any possible repair. This reality forced engineers to adopt a design philosophy centered on redundancy and fault tolerance. Backup systems shadow primary ones. Self-diagnosing software can work around failures, and critical components have multiple operational pathways, ensuring Webb can adapt and survive without human intervention. Throughout the structure, specialized materials resist the degradation that would quickly destroy conventional components exposed to the harsh radiation and vacuum of deep space, allowing Webb to stand as humanity's enduring sentinel at the solar system's edge. As our journey through the cosmos with the James Webb Space Telescope comes to a close, we're left with a profound appreciation for what NASA officials describe as the critical importance of maintaining its position at L2. This invisible battle against cosmic forces forms the foundation that makes every breathtaking image possible. With careful fuel conservation and precise station-keeping maneuvers, Webb's lifespan could extend beyond 20 years. 2 decades of peering into the universe's most distant corners, all made possible by an observatory balanced on the edge of chaos, dancing around nothingness with mathematical precision. What cosmic mysteries await us as Webb continues its celestial waltz at L2? If you're as fascinated by space as we are, you won't want to miss these other videos. We dive even deeper into the universe's secrets and explore recent discoveries that could revolutionize your understanding of the cosmos. Thank you for joining us on this cosmic adventure. Stay curious and keep looking up.